sequence. If A is a set, by a sequence in A, we mean a function f from the set of natural numbers to A. For each n in n, let x sub n equals f of n. Then x sub n is called the nth term of the sequence f. For example, let f is a map from n onto n. Here A is n. Defined by f of n equals 2n. By notation, this is denoted by x sub n. So f of n equals 2n. Then the set f contains the elements 2, 4, 6, 8, and so on. In short, all the positive even integers. And this is a sequence in n, because when we put 1, we get 2. When we put 2, we get 4. When you put 3, we get 6. So we are substituting 1, 2, 3 here, and we are multiplying it by 2, so we get the even positive integers. This is a sequence in n. For notational convenience, sequences are denoted by this symbol, or just by this symbol, without any subscript or superscript. So the terms are enclosed within the curly braces, rather than by using the function f itself. For example, the previous sequence defined by the function f of n as 2n can be written simply as 2n enclosed within the curly braces. So this is a sequence in n. Namely, the sequence terms are 2, 4, 6, 8, and so on. Now we state some theorems. Every infinite subset of a countable set is countable. If f maps the set of natural numbers onto some set A, then the set A is at most countable. In other words, if f be a function from the set of natural numbers n onto A, then either A is finite or A is countable. These two are collectively called at most countable. Please read the proof in the notes or in the textbook. Let P of x denotes the set of all subsets of a set X. Means this is a power set of a set X. Let A and X be non-empty sets. A function f from a set A into the power set of X is called an indexed family of subsets of X with index set A. The index set may be finite or infinite, countable or uncountable. Let's have a look at an example. Let A is a set of these 3 elements and X of a set of these 2 elements. Then the power set of X is a set of all possible subsets of the set X, namely the set containing A only, the set containing B only, the set containing A and B, and the empty set. So if we have 2 elements in the set X, its power set must contain 2 to the 2 many elements, namely 4 elements. Now we define a function f from a set A to the power set of X as follows. F at 1 equals, for example, the set containing B only. F at 2 equals the set containing A and B. And f at 3 equals this set containing A only. That is, for each alpha in the set A, f of alpha equals some set E with an index alpha, where E alpha is an element of the power set of X. In other words, f of 1 is a set E1, which is, as defined, the set containing B only. Similarly, f at 2 is some set E sub 2, which is defined as a set containing A and B. Similarly, f at 3 equals E sub 3, containing A only. Another example. Let A is a set of real numbers in between 0 and 1, the open interval. Now, for each x in A, let's define a set E sub x this way. So E sub x is a set of all rational numbers R such that R is larger or equal to 0, but strictly smaller than x. For example, E half would be the set of all rational numbers such that R is larger or equal to 0, but strictly smaller than half. Then the function f from A to the power set of the set of rational numbers defined by this f of x equals E sub x. This is an indexed family of subsets of Q with an indexed set A. If A, the index set, equals the set of natural numbers, then this set, collection of E sub n's, is called a sequence of subsets of X. So this collection contains E sub 1, E sub 2, E sub 3, and so on. This is called sequence of subsets of X. And we will use more conventional notation, this, to denote this set, the index family of subsets of X. Suppose this is an indexed family of subsets of X. The union of the family of subsets is defined to be this way. So in the left hand side, we have the notation for the union of all the elements in the family, where alpha is an element of the index set A, is a set of all X in the set X such that X belongs to E alpha for some alpha in A. Similarly, the intersection of this family of subsets is defined to be this way. The intersection of this family is a set of X in X such that X belongs to E alpha for all alpha in A. Again, if the index set A equals the set of natural numbers, we will use the notation, this notation for this symbol. So this is the countable union of the family of subsets of X. Let's consider an example. If A is a set and X is this set, and F, as defined earlier, from A into the power set of X, f of 1 equals E sub 1, which was the set containing B only, and f of 2 is this set, and f of 3 is this set, then the union of this family of subsets gives us the set containing A and B only. And the intersection of this family of subsets is an empty set, which is clear from these three sets. Another example. If A is the open interval from 0 to 1 and E sub x as defined earlier with the function f from A to the power set of Q as f of x equals E sub x, then the union of this family of subsets of the rational numbers Q is simply E1. And the intersection of this family of subsets is simply the set containing the element 0 only. Please pause the video and try to verify these two results. For the arbitrary union and intersection of family of subsets of X, we have the following distributive laws. Suppose E is some set. Then the statement A says E intersection, the union of E alphas would be equal to the union of E intersection E alpha. B says E union, the arbitrary intersection of E alphas is equal to the set, the arbitrary intersection of E union E alpha. Another theorem, De Morgan's laws. The complement of the arbitrary union of the family of subsets of X would be equal to the arbitrary intersection of the complement of the family of subsets of X. Similarly, the complement of the arbitrary intersection of E alpha would be equal to the arbitrary union of the complement of the sets E alpha. Theorem: let f is a function from set X into the set Y, then the following statements hold true. Please try to read the proofs in the textbook.